Okay, so last time we considered sets, and some of the sets that we considered had infinitely many elements, and some of them would have had finitely many elements. And I would, in this session, I'd like to consider sets that have finitely many elements. And counting exactly how many elements they have. Okay. This will be important later when we assign probabilities to these sets. So we're going to go over a few rules of counting. Okay. So the biggest rule is the multiplication rule. And what this rule says is, well, we'll give an example before we say what it says. Supposing I want to toss a coin twice, okay? And so I'm going to count it, I'm going to toss it, then I'm going to record the result. Then I'm going to toss it again, and I'm going to record the result. So the first toss, you either get a head or a tail. And then after getting a head or a tail, what do you get? Well, you could get a head or a tail, or after tossing a tail, you could get a head or a tail. Okay. Now, the result of this experiment could be head, 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 tail, tail, head, and tail, tail. Okay. Now, how many possible outcomes are there for this experiment? Well, there are 4 possible outcomes. Okay. Right. And we noticed that this was a 2-step. This experiment involved 2 steps. And the first step could result in 2 outcomes. And then the next step could result in 2 outcomes. And 2 times 2 is 4. And we said that there were 4 possible outcomes in this experiment. Okay. Well, what if we roll a 6-sided die twice? And I'm going to record the result that I get. So I roll it once and I record the result. And I roll it again and I record the result. Now, how many possible combined results are there for this experiment? Well, the first step of the experiment takes 6 steps. The first step of the experiment has 6 possible outcomes. The next step of the experiment has 6 possible outcomes. So when we put them together, we have 36 possible outcomes. Okay. So now let's state the multiplication rule. So supposing an operation can be performed in 2 distinct steps, the first step can be performed in n1 ways. And then for each of those n1 ways, a second operation can be performed in n2 ways. Then the combined operation can be performed in n1 times n2 ways. Okay, so the coin toss experiment is one experiment, right? So the first step can be done in 2 ways. And then for each of those 2 ways, the next step can be done in 2 ways. So 2 times 2 equals 4. For the roll of the dice, the first step, the first roll, that can result in 6 possible outcomes. And then each one of those possible outcomes can also have, again, be followed by 6 possible outcomes. So 6 times 6 is 36 possible outcomes for the completed experiment. All right, and in general, this expands to n1 times n2 up to nk. Let's say that the experiment requires k steps. Okay. All right, so let's try something. If I have 5 different shirts and I have 7 different pants, then how many shirt pant outfits can I wear? Okay, so here, what's the experiment? The experiment is to pick a shirt and to pick a pant. Well, there are 5 ways to pick the shirt, so 5, and then there are 7 pants that I can pick in the next step of the experiment. If I put that together, then there are 35 possible outcomes to this experiment. Okay, here's another one. So let's say we have 2-digit numbers, and we're not using 0. So you pick the first number is pick 1 through 9, and the second number is pick 1 through 9, but you can use each number only once. Okay, so I have to pick a first number, and I have to pick a second number. The numbers I'm allowed to pick are the digits 1 through 9, and I'm not allowed to use a number twice. Okay, so how many ways are there of doing this? Well, to pick the first number, I have 9 possible choices. So there are 9 ways of performing that first step. The second step is to pick another number, except I can't use another number again. So there are 8 numbers left over to pick from. So the first step can be done in 9 ways, and then for each one of those 9 ways, there are 8 ways of doing the next step. So 9 times 8 is 72. Okay. Let's try this again. And let's say that I'm going to insist that you have to have a 2 for the first digit. So how many ways are there of performing the first step and picking the first digit? Well, there's only one way. You have to pick the 2. I've insisted on that. So that's 1. And then for the second step, I can pick the numbers 1 through 9, but I'm not allowed to use 2 again. So there are 8 left over. So there are 8 ways of performing the second step. 1 way of performing the first step, 8 ways of performing the second step. So 1 times 8 is equal to 8 possible outcomes for this experiment. Okay, now the set of all possible outcomes was, remember, there was 9 times 8 is 72 in the first time we did this. We considered these 2-digit combinations. And then when we insisted that we had to have a 2 in the first case, in the first digit, then there were 8. So 8 over 72, 1 to 9. All right. So we need to keep the multiplication rule in mind sometimes. Okay. Next, we come to the idea of permutations. So this is more along. This is concerns the number of ways in which some things can be done. Okay. And a permutation is the arrangement of all or part of a set of objects. That'll become clearer when we do a few examples. Okay, so let's consider the letters A, B. Okay, they can be rearranged as BA. So let's say, how many ways can I write the letter A and the letter B in a row like this? Well, I can either write them as AB, or I can write them as BA, and there are no more permutations. So there are 2, we say that there are 2 permutations of the letters AB written as one word. Right? In this case, the word is a nonsense word, but we'll call it a word. Okay. Okay. So there are 2 permutations of 2 distinct letters written together. Okay. Now, supposing I have the letters A and B and C, and I want to write them together like this. They should be written ABC or BAC or CBA or, okay. Now, how many permutations of these three letters are there? Okay, let's use the multiplication rule to do this. I have to pick a first letter. I have to pick a second letter. I have to pick a third letter. How many ways are there to pick the first letter? There are three letters to pick from, and I pick one of them. Now, how many ways are there to pick the second letter? Well, I already picked one of them, so there's two letters left over. So there's two ways to pick the second one. How many ways to choose what to write into the third slot? Well, I picked the other two letters already, so there's one letter left to write. Okay, so 3 times 2 times 1 is 6. There are 6 permutations of the three letters ABC. Okay. Well, what if I had 4 symbols, not necessarily letters? I have 4 distinct symbols. I'm just going to write them in a row, okay? As if I was writing a word, and I just write them all together. So I have to pick a first symbol, a second symbol, a third symbol, and a fourth symbol. And they're all distinct. Okay? 4 ways to pick the first symbol, 3 ways to pick the second symbol, 2 ways to pick the third symbol, and 1 way to pick the fourth and last symbol. So 4 times 3 times 2 times 1 is 24. So there are 24 permutations of 4 distinct letters. Okay, one convenient notation here is the idea of a factorial. So we define a factorial, we define 0 factorial to be 1. And then for an integer n, a positive integer n factorial is n times n minus 1 factorial. Okay, so and you count down to 1 or to 0. Okay, so 3 factorial would be 3 times 2 times 1. 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1. Okay. All right, so permutations of 4 distinct symbols. If I use this factorial notation, it's 4 factorial. For n distinct symbols, it's n factorial. Permutations of n distinct symbols. Okay, so let's say I have 4 distinct symbols, and okay, so if we come back to the 4 distinct letters example, 4 distinct symbols, A, B, C, D. How many possibilities are there to? So we have 4 distinct symbols to choose from, and we get to choose 1 single letter. Okay. So how many possibilities are there? Well, there are 4. And 4 turns out to be equal to 4 factorial over 4 minus 1 factorial, right? Right? If you have 4 factorial and you divide by 3 factorial, you are left with 4. Now, let's say you want to, let's think about it this way. You want to arrange 4 objects. So there are 4 permutations of these distinct objects, which is 4 factorial. but the three which were not picked, they can be arranged in any way, right? So we've in fact overcounted by 3 factorial. So that's another way of looking at the same thing. 4 factorial divided by 3 factorial. Okay. Continuing with the same example, we have 4 letters, A, B, C, D. 2 are to be picked for a 2-letter code, and the order matters. A letter can be used only once. Okay. Well, for the first step, I can pick 4. And for the next step, I could pick 3. So there are 4 times 3 ways of doing this 2-letter code. Okay. Now, if I want to write it in terms of factorials, that would be 4 factorial divided by 2 factorial. That's also 4 times 3. Okay. Or another way of looking at it is there are 4 factorial ways to arrange 4 distinct symbols. But the symbols that we don't pick can be arranged in any way. How many symbols are there we didn't pick? 4 minus 2. Right? So if we say 4 factorial, then we've overcounted by 4 minus 2 factorial, so we should divide by that. Okay, so that's 4 factorial divided by 4 minus 2 factorial. Okay, so rules for permutations. The number of permutations of n distinct symbols taken r at a time is n factorial divided by n minus r factorial. And we use this notation npr, which some people read as n pick r. Right? And remember, this is here we're thinking of the order as mattering. Okay. When we come to cases where you have choices and the order doesn't matter, then we'll discuss that some more. Okay. So the number of permutations of n distinct objects taken r at a time is n factorial divided by n minus r factorial. Okay. So there are 30 distinct symbols, 2 are to be picked, and the order matters. So how are you going to pick those? That would be 30 times 29 according to the counting rule. Okay. Now, the other way of looking at it is to say that it's 30 pick 2 in order, and then the rule is 30 factorial divided by 30 minus 2 is 28 factorial. And note that 30 factorial divided by 28 factorial is 30 times 29. Okay, there's a little bit of a technicality. If you here we're arranging the symbols in, say, in a straight line. Let's suppose that you arrange them in a circle. Why is that different? If you have n distinct objects that are arranged in a circle, there are only n minus, rather than n factorial permutations, there are n minus 1 factorial permutations. Okay. I'm going to let you think about that, why that is. Okay. Let's try another exercise. How can 7 people be seated around a table for dinner? It's a circular table. 7 minus 1 is 6 factorial. Okay, Now, let's say we have non-distinct objects. So we have to be a little bit careful. So let's say we have two letters to write a word, and both we want to write a two-letter word, and both the choices we have for the letters are A and A. So if you're going to permute, you have your A, and then you interchange the two symbols, it still spells the same word, right? So there's only one permutation of one symbol taking place. Okay, but if you had A and B to write a two-letter word, then you could write two-letter words with it. Okay, so the fact that your symbols are distinct or not distinct is going to affect your answers. Okay, so supposing I have these letters A, and B, and I can rearrange them to make a three-letter word. Each letter can only be used once, and two of the letters are identical, right? So I use the first A, I use the first B, and I use the first A, I use the second A, and I use B, right? And I can't use the first A or the second A or the B over again, okay? Now, how many ways can I do that? Well, one way of looking at it is to say, once I decide where the B goes in the word, then everything else is fixed, right? So it's BAA or ABA or AAB. And there are no other ways of doing that. So my answer should be 3. How about if I use the ideas that I've been using before? Let's suppose that the symbols were all distinct. Then there would be 3 factorial words that I could write. However, 2 of the letters are in fact the same. So if I interchange those, then nothing changes. It's not a new word. Okay, but when I said 3 factorial, then I was actually claiming that it would be a different word. So I've overcounted. So I overcounted why? Because I thought that those 2 symbols were distinct. I was treating the 2 symbols as if they were distinct. And if they were, the interchange of those, there would be 2 factorial ways of interchanging those symbols, which are in fact not distinct. So I've overcounted. If I say 3 factorial, I've overcounted by a factor of 2 factorial. So I should divide that out. Okay. So it should be 3 factorial divided by 2 factorial would be the correct answer. Okay. So if we then generalize, let's say I have n total symbols. One of the symbols, there are n1 copies of one of the symbols, there are n2 copies of one of the symbols, there are nk copies of the kth kind of symbol. Okay, so n1 plus n2 plus n3 adds up, let's say, to a total number of n symbols. So if I look at the number of permutations of one symbol after another, and if these were all distinct, there would be n factorial of those. But n1 of them are the same, so I've overcounted by a factor of n1 factorial. And n2 are the same, so I've overcounted. When I said n factorial, I was overcounting by n2 factorial, and so on. So then I divide out to take care of that overcounting. So I have n factorial over n1 factorial, n2 factorial, up to nk factorial. Okay, so as an example, I have 3 white billiard balls and 3 black billiard balls, and they're going to be laid out in a line. So how many distinct permutations can I make? Okay, well, there are 6 possible symbols. If they were all distinct, we would have 6 factorial. But 3 of them are the same, so I should divide by 3 factorial. And another 3 of them are the same, so I should divide by another 3 factorial. So by this rule, this is 6 factorial divided by 3 factorial, and again divided by 3 factorial. Okay, so permutations, partitions. Okay, so here's an example of a partition before I define what a partition is. Let's do an example to get the idea. Okay, so I have 12 chutes. I have an upper drawer and a lower drawer. So how many ways to put 6 shirts? Okay, so let's say that the shirts are distinct. Okay, so how many ways to put 6 shirts in the top drawer and 6 shirts in the bottom drawer? And within that drawer, we don't worry about the order that I put it on the left or the right or whatever. Okay, so I can mix up the shirts. Once the 6 shirts are in a drawer, I can mix them all up. I don't think of that as being a distinct arrangement. Okay, so how many ways to do this? Okay. Well, the way we think about it is there are 12 ways to arrange 12 symbols. So I can imagine that I lay my shirts out, and then I put a line here so that there's, okay, divide them up into 2 groups. So if I didn't put the line and I laid out 12 shirts on my bed, right? And in a line, I could say, well, there are 12 factorial ways going from left to right, arranging them left to right. There are 12 factorial ways of arranging these 12 different shirts. And then I said, well, okay, I'm going to put a line here down the middle. So there's 6 on one side and 6 on the other side. Now within, right, that's the same as saying, okay, I'm going to put these 6 in this drawer, and I put these 6 in this drawer. Now within the drawer, I don't care how I arrange them. Well, there's 6 symbols in there, and I don't care how they're being arranged. So when I said 12 factorial, I was overcounting by 6 factorial. And now when I look at the next drawer, there are 6 shirts, and I don't care how they're being arranged. And so when I said 12 factorial, I was overcounting by another 6 factorial again. So the answer is 12 factorial divided by 6 factorial, and then divided by 6 factorial again. Okay. Right? So, and let's say that this time I had 12 shirts. I have an upper drawer and a lower drawer. I put 7 shirts in the upper drawer, and I put 5 shirts in the bottom drawer. Order within the drawer, how I arrange them within the drawer doesn't matter. Okay, so how many ways are there of doing that? Well, if order mattered, and I was laying them out in a row, there would be 12 factorial ways of doing it. Now I've put them into, when I put 7 of them into a drawer, and then the order doesn't matter anymore, you're saying, then that they, and that 12 factorial included 7 factorial arrangements of those shirts, except I'm not regarding those as different ways of arranging the shirts anymore. So I should divide by 7 factorial. And in the bottom drawer, when I said 12 factorial, well, there were 5 factorial ways of arranging these shirts, except now I'm saying that it doesn't matter if I interchange the shirts or rearrange them in any way. So that 5 factorial is overcounted. So I've overcounted by 7 factorial times 5 factorial when I said 12 factorial. So this is 12 factorial divided by 7 factorial and then divided by 5 factorial again. Okay. So now let's be specific of what we mean by a partition. We may be concerned with partitioning n objects into R cells, and within each cell, the ordering doesn't matter. Okay, so how do you do that? So this is then, well, n objects, n distinct objects can be arranged in n factorial ways. And then when we look at how many we put into the first cell, if there were n1 of those, then we've overcount, and the ordering within that cell doesn't matter. Then we've overcount, when we said n factorial, we overcounted by n1 factorial. And then we said n factorial, but there were n2 distinct objects in the second cell. And we're saying that the ordering within that second cell doesn't matter. So in this n factorial, we overcounted by n2 factorial, and so on. So in this, if you have n objects, which are to be partitioned into R cells with ni in each cell, in the ith cell, in which ordering doesn't matter, then the number of ways there are of doing this is n factorial divided by n1 factorial, n2 factorial, up to nr factorial. Okay. Let's try another one. So there are 52 cards in a deck, so there are 52 distinct cards in a deck. How many ways are there to give 13 cards to each to 4 players? Well, when I hand you your cards, you pick them up. And then when you rearrange the cards in your hands, it doesn't matter whether you, I mean, that's just according to your convenience, right? It doesn't matter how you arrange those cards that you're holding. That's still regarded as the same hand, right? So what we're doing is we're partitioning 52 cards into 4 cells. 4 players are holding them. And the order that that player holds each card, their cards, doesn't matter. So 52 factorial cards, considering them to be all distinct, they are. But then divide by 13 factorial for the first player. There are 13, he's holding 13 cards. Then 13 factorial for the next player. Then 13 factorial for the next player. Then 13 factorial for the next player. So it's 52 factorial divided by 13 factorial, 13 factorial, 13 factorial, 13 factorial. Okay. So combinations now. Combinations are a type of partition, all right? Except the case of partitioning into 2 sets, into 2 cells, comes up so many times that we give it a particular name, combination. Okay. And we have this notation. We read this as n choose r is equal to n factorial divided by r factorial times n minus r factorial. Okay? So n choose r means, supposing that I've got n things, and I'm going to choose r of them. So what am I doing? I'm taking those n things and I'm separating them out into 2 cells. One cell will have r, and the other cell will have n minus r. And I'm not considering the ordering in either of the 2 cells, neither the r objects that I've picked up, that I've chosen, nor the n minus r that I've left behind. So by our rule for partitions, the number of ways of choosing r objects, r distinct objects from n distinct objects, that's equal to n factorial divided by r factorial, n minus r factorial. Okay, so how many subsets of no elements are there of a set of n elements? That's a little bit tricky. There's one. There's one empty set. Okay. So n choose 0. Right? N choose 0 is equal to 1. If you come up here, you let r be equal to 0. N factorial divided by 0 factorial divided by n minus 0, n factorial. So n factorial divided by n factorial is 1. Okay, how many subsets of k elements are there of n elements? Well, how do you make a subset of k elements? You choose k elements from the set of n elements. So how many ways are there of doing that? N choose k. Right. And it turns out that if you add up all of these symbols n choose k from k equals 0 to n, you're going to get 2 to the n. You might recall this from an algebra class. Okay, so there's a bit to digest there, and you need to do some exercises. Okay, so you should the file lecture 02 EX, I think I called it, in my Google Drive. That gives you some exercises that you should do to practice. Okay. So I will see you next time.